All right, good morning, folks. Couple announcements. First of all, I just want to point y'all, I am posting the screencast for the class. Sometimes they don't work out or whatever, like if they fail during class, I can't redo it. But I just do want to remind you that on the website, that if you follow this online quizzes link, that it has all the screencasts. And I've been updating it for this chapter. So like, I haven't finished all the material, but I've finished a lot of the material. So if something here just doesn't sit well with you or you're not sure what the answer is, you can go and sort of catch up on the material from that section, okay? And then also, we will not have Quiz Friday this week. Or would y'all rather, we're going to have it next week. I can either have it on Friday or next Friday. How about I just put it up today, and then you can finish it this Friday if you want, or you can finish it next Friday. That will be the last quiz. And the response is sadness. Oh, just one more, right. And then I'll put it up today or tomorrow, but it'll be new next Friday.
How many points are you dropping?
Didn't I say 2? Yeah. The top.
So if we like off on the
What's that?
Like, so it's going to off quizzes total, like, for points?
I don't know. How many quizzes do we have total? I think we had 8 or 9 quizzes total.
Okay.
And so whatever your percentage is, I'll just take that. I'll drop your 2 lowest scores, take a percentage. So if I drop your 2 lowest scores, your percentage will go up. And then take that percentage of 50. I think it was worth 50, the reading quizzes.
Okay.
Or the extra practice quizzes.
Are you calculating for these for final grade? Just like put that factor in there to a drop?
I don't think so. So that was sort of a lower estimate. Or maybe I did, but I was assuming I didn't know what you were going to make on upcoming quizzes. But you should make perfect on the next one, and that'll raise up that projected score. Okay? All right. We will have a day off next week, and I'll let you know. I don't know what day that is. Y'all have a preference? I'd rather not do Monday. Friday? All right, we'll probably do Friday. Or no, you know what? I'm just going to decide.
Friday.
I'll send you an email. We might do a help session on Friday in class, because we have an exam on Monday. Okay? I'll send you an email. I'll let you know. So we're looking at the production of sound. Sound waves are created by some object pushing on the air. So for example, you ever seen a speaker? A speaker is basically like a paper cone, and then you have like a little actuator on that cone, and then attached to that actuator you have like a magnet, and it takes an electrical signal. Electrical signal comes into that magnet and causes the magnet to vibrate or to vibrate that paper cone, and this paper cone physically pushes the air, and so it creates these areas of high pressure, low pressure, high pressure, low pressure, high pressure. So this is a high pressure, this is low, this is high, this is low, and this is high. In fact, remember, I don't know if I said this, but sound waves, we have several different names for sound waves, or several different types. They're longitudinal, not transverse. Should already have that written down. There are also pressure waves. Did we call them pressure waves before? Yeah, so they're also pressure waves, and for this reason, because they change the pressure of the medium that they're traveling through, whether it be air or whether it be a liquid or a solid. They have to change the pressure. And then eventually this pressure wave, gets over to your ear, and that pressure wave inside of your ear, and we'll talk about this later. And all of y'all have had anatomy, is that right? No? Okay, we'll talk a little bit about the ear. You should get into the ear when you take anatomy. But the ear is an eardrum, or the tympanic membrane. It's like a timpani. You ever seen a timpani? Those big kettle drums that they use in the orchestra? And it pushes on this. When I have a high pressure, it pushes it in this direction. When a low pressure encounters it, it pulls it in that direction. And then your eardrum vibrates, and those vibrations are transferred into first a pressure difference in a fluid, and then an electrical signal. We'll talk about all that, how the ear works. It's actually pretty cool. Okay, so that's how we actually produce sound, is by pushing on the air. goodness. You okay? A simple wave, there aren't many simple waves, but a simple wave has a single frequency. So a simple wave might look like this, just with a simple frequency, but a complex wave, which is basically most sound waves that we have, will have multiple frequencies added up. So for example, let's say that I have two different frequencies. I have a wave of this frequency, and then I add it up with another wave of a much higher frequency. Now if I add these two waves, it's going to look something like this. It might be a little more complex, but it's going to look something like this. You're going to see the two waves superimposed on one another, where I have the high frequency signal mixed in with the low frequency signal. But you know what, in practice, like all sounds that we hear, musical sounds and from our voice, they are a mixture of many different frequencies together. I do want to show you just what happens when you mix, say, just two frequencies together, because it's fairly interesting, and it does come up in your homework. Let me just show you first of all, and then I'll explain to you. You can go online and find these online tone generators. I just Googled online tone generator, and there's a bunch of them out there. And it allows you to play sounds of different frequencies. So this sound is 118 hertz. Let me turn that down. That's not too annoying, right? Now, do y'all know what the do you know what the range of hearing for human beings is? The range of hearing goes from about 20 hertz is the lowest we can hear, up to about 20,000 hertz. And then beyond that, humans can't really hear beyond 20,000 hertz. And in fact, as you get older, you begin to lose that range as well. Or if you've had hearing damage or whatever, you attended too many Megadeth concerts or whatever, then you can have hearing loss because you've been exposed to sounds that are too loud. So let's see where you stand. I'm going to raise this up to 20,000 hertz. I'll play it. You might hear that. Let me turn it up a little bit. How about now? Okay. Not many people can hear 20,000. Let's just go down. Anybody? Yeah, can you hear it really? Is it really annoying to you? Yeah, let's go down a little bit more. We'll annoy the rest of us. Okay, I'm sorry. Yeah, so we'll go up. Let's turn the volume down. Okay, that's where I drop out. Can anybody not hear that? Y'all can hear it? Yeah, okay. I'm sorry. That's really annoying, right? I'm sorry. It's very difficult to get low frequencies on these speakers because our speakers are only about this big, although these are a pretty nice sound system in this room, but 20 hertz is a very low sound. You need a nice big amplifier with a big old woofer to get 20 hertz, so we're not even going to try with that. So let's find out now what happens. That's a nice comfortable tone. It's 150 hertz. Let's see what happens when I add another tone of 150 hertz. Okay, so now I'm adding up two tones. They're both 150 hertz. They add up, just, they're the same frequency. But watch what happens when I just change one of these by just a little bit. Those are called beats. How often are those occurring, do you think? About how many a second? 30 a second? It's about 1 a second. 1, 2, 3, 4, 5. All right, they occur at 1 a second. 1, 1, 1, 2, 2. These are 2 a second. These are 3 a second. and 4 a second. So any of you play, I know a few of you play stringed instruments. That's how you tune a guitar or piano or whatever. If you take some known frequency, like if you're tuning a piano, you take a tuning fork and dum, and then you pluck the string, dum, and if you don't get any beats, if you don't get any wah, wah, then that means that those two frequencies are exactly the same. But if they're off even up by just a little bit, even by just a single hertz, which is just a tiny little bit in space, a frequency space, then you'll hear this very distinctive beating sound. Wah, wah, and it allows you by your ear to tune something like a piano or a guitar or whatever. So like with a guitar, you play an A on one string, and then you play an A on the other string, and then you tune the string until they sound exactly the same, until you don't hear that beat sound. We can determine the number of beats if I have two frequencies. We can determine the frequency of the beat, and the frequency of the beat is just equal to one of the frequencies minus the other frequency, and we just take the absolute value. So when I had two frequencies that were just 1 hertz off, they had a frequency of 1 hertz. If they were 2 hertz off, they had 2 a second. 3 hertz off, 3 a second. Bless you. Okay? So that's beats. They occur because we get this superposition of waves, and they create a signal that's something like this. So yeah, this signal, by the way, would have many beats because the frequencies are so different. All right, let's look at the intensity of sound. Sound carries energy like all waves. To characterize the energy, we measure the intensity. Now be careful, because we're going to be dealing with two different things. We'll be dealing with the intensity, and then we'll be dealing with the intensity level. Those are related, but they sound a lot alike. Intensity and intensity level. First, we're going to look at intensity. Intensity is defined as the P over A, where P is the power, A is the area. Remember power, we've done this before, but the units are in watts, and area, the units are in meters squared, and so the units for our intensity are going to be watts per square meter. Remember, this watts is an energy per unit time. Right, we talked about power last semester and then again this semester in terms of electrical energy. So our intensity is power over area. If we assume that the source is a point source, that is, say I have a speaker that emits sound in all directions, it's emitting this sound wave in all directions, then we can write this intensity as the power divided by the area of the surface that is filled by this sound wave. So if it's going out in all directions, if I'm at a certain point a distance away, what kind of surface am I dealing with over which that sound energy is spread? It's a spherical surface. So the intensity then, if I'm dealing with a point source, is going to be the area of a sphere, and the area of a sphere is 4 pi r squared. So my intensity is our power divided by 4 pi r squared. Where here r is just the radius of the sphere. And because of this, as r increases, I drops a lot. It's an inverse square law, and if I were to plot I versus r, then it looks like this. It's an inverse square law. As r increases, I decreases as a factor of 1 over r squared. So like, for example, if I double r, if I move twice as far away from that speaker at the Metallica concert, or whatever it is that you don't know. I mean, are they even alive still? I think they are. But anyway, whatever it is that you do, if r doubles, then you get 1/4 the intensity. So it's a good idea to get away from those speakers. Oh, and by the way, too, if you have a source that is not spherical, that is, say you have a megaphone or something, like you're at a football game and one of those cheerleaders comes up to you with a megaphone and yells right into your ear, remember, that doesn't spread over a spherical surface. So instead, you're dealing with an area that is much smaller, so it's much louder than it would be if you were just, somebody was just yelling out into space. Okay? Because it's directed towards you. And it's not spread over a large area. All right. Let's try these quick tests. We'll try the one on the left first. Did I tell you on the Batman joke? I told my family that joke, and they didn't even think it was funny. And I told them that y'all thought it was like hella funny, right? Didn't you think it was really funny? They didn't even think it was funny at all. They didn't even know what it meant. Get in the car. I know, good. That was a good joke. All right, folks, focus on this question. We're doing the one on the left, okay? Doing the one on the left. Alrighty, I'll stop at 120. We're doing this one, 120, 5 more seconds. Okay, D is right. Remember, our intensity is power over area. That's power over 4 pi r squared. So if I double r, which is what I'm doing, I'm going from 1 meter to 2 meters, so I'm doubling r. That means I'm going to have 1 over a fourth of my original intensity. So D is the right answer. A lot of you put E, but remember it's not an inverse law, it's an inverse square law, inverse square relationship. And then how do we define intensity? One on the right. All right, I'm going to stop at 30 seconds. 30 seconds. Oh. Okay, awesome. D is right. Power over area. Oh, it's right there, right? Intensity is power over area. Let's do some of the clicker questions. Listen, I'm sorry I didn't send y'all the papers that you could print out, but we're just going to do a few of them because we're sort of getting ahead of ourselves, and then I will send it out to you today. I'm very, very sorry about that. I know some of you like to have those printed out, but I will send them out to you today. Okay, so waves. These aren't in the back of your book. Am I right? They're not in there, right? It's because I messed up. I didn't get them to you. I've already asked for your forgiveness. You gave it to me. We're good to go. Waves propagate along a stretched string with a speed of 8 meters per second. The end of the string is vibrated up and down once every 1.5 seconds. What is the wavelength of the waves that travel along the string? All right, we'll stop at 125. Just 5 more seconds. Just guess if you're not sure. I'll go to 128. 128. All right, B is right. You're picking out here. This is our period. If the string moves up and down in 1.5 seconds, that's our period. So T is equal to 1.5 seconds. And then our speed of the wave is 8 meters per second. And remember, our speed is lambda over T, or you can think of it as lambda times our frequency. But our frequency is 1 over the period. And we're looking for the wavelength. So our wavelength is V times T, which is 8 times 1.5, or 12. Bats can detect small objects such as insects that are of a size approximately that of 1 wavelength. So their resolution of things that they can detect is about a wavelength. They emit a sound at 60 kilohertz. The speed is 330. What is the smallest size insect they can detect? While you are thinking about this, I'm just going to remind you that your metric prefixes on this next test are going to be more important than they were on the previous test. So I'm just going to remind you those metric prefixes. I have kilo, which is 10 to the third. We're not really going to, we're not going to deal with, no, we might. Kilo, mega is 10 to the 6th. Giga is 10 to the 9th. And then on the low end, we have centi is 10 to the minus 2. Milli is 10 to the minus 3. Micro 10 to the minus 6, and nano 10 to the minus 9. If you're not adept at converting back and forth between those, make sure that you review that, because it'll be important on this next test. I'll stop at 140. 140. Okay, good. C is right. Our frequency is 60,000 hertz. Our velocity is 330, our wave speed. And then we're looking for the wavelength. That's going to be V over F, which is 5.5 times 10 to the minus 3. You find that to be in meters, which is going to be 5.5 millimeters. We'll see that that's true too also for ultrasound, that the resolution of an ultrasound is about the wavelength. 5.5 millimeters, I mean, that's itty bitty. That bat can see things that are about that big with this echolocation. 5.5 millimeters, that's not much. It's a half a centimeter. It's pretty amazing, actually. Y'all seen that guy on YouTube that can echolocate? I'll show you. Isn't that cool? He like makes these chirping sounds, and he can see things in his mind. Like he can tell that there's a tree or a person or something like that. We'll talk about it later. I'll show you. It's pretty cool. If the frequency of a traveling wave is increased by a factor of 3, where the velocity is constant, which of these is the result? The frequency is increased by a factor of 3. All right, we'll stop at 40. 6 more seconds. Awesome. C is right. Our velocity is equal to our wavelength times our frequency. If the frequency goes up by a factor of 3, this has to go down by a factor of 3. So C is the right answer. This morning, I was making lunch, and I had to chop up some cheese, and I cut my finger while I was cutting up the cheese. You know, I think I have a greater problem. Uh-huh. A gust of wind blows across a field of grain. The plant's going to be seen to wave back and forth, back and forth. This wave is which of these? Transverse, longitudinal, polarized, or is it interference of waves? All right, we'll stop at 42. 42. Awesome, B. So longitudinal waves, remember the difference between longitudinal and transverse. Transverse make your medium go up and down, up and down. Longitudinal make them go side to side, like when y'all, you know, hugged one another. Oh, did you hear the joke about the wall? It's hilarious. I'm still trying to get over it. You didn't hear that one? Yeah. All right, for a wave on the ocean, the amplitude is which of these? Remember how we define amplitude? All right, I'll stop at 35, 35. All right, good. C is right. It's 1/2 the distance. So if I'm looking at an ocean wave, I can measure this distance readily, and my amplitude, though, is 1/2 of that total distance. My amplitude is the distance from our equilibrium position up to the peak of the trough. So it's not B, it's not A, that would be the wavelength. D is just gibberish. So it's C is the right answer. Gibberish, yes, excuse me. All right. A radio wave has that speed. Remember, it's a light wave. The frequency is 107.7 megahertz. It's 10 to the 6th. What is its wavelength? All right, I'll stop at 1 minute. 1 minute. I guess so. Let's see. So my frequency, I want to know the wavelength. So the wavelength is the speed over the frequency. That's 3 times 10 to the 8th over 107.7 times 10 to the 6th. This gives me a 2. Yeah, that looks right. Is D is right? Yeah. Yeah. Okay, we will come. Actually, have we done this yet? No, we'll come back to this. We have done this, but we will come back to it. And I will mail that out to y'all. I'll send it, or put it on Moodle and send y'all a message. I'm going to send you a normal Wednesday message anyway today. Okay. When we're talking about intensities, we need some way to convey it into what we actually hear. And so we need to define 2 different reference points, the threshold of hearing and the threshold of pain. The threshold of hearing, that is the lowest sound that you can hear, not the lowest frequency, but the lowest intensity. which you remember is related to your amplitude. The threshold of hearing is 10 to the minus 12 watts per square meter. And then the threshold of pain, the sound that you hear, same frequency, but when it starts causing pain in your ears, is 1 watt per square meter. 10 to the minus 12 and 1. These aren't numbers that you need to memorize. I'll give them to you as you need them. Think about that there. 10 to the minus 12 is the lowest sound that you can hear. 1 watt per square meter is the loudest sound that you can hear. That's 12 orders of magnitude, right? That you can hear over 12 orders of magnitude. Doesn't that seem amazing here? That is quite amazing, actually, that you can hear sounds over such a large range of intensities, over 12 full orders of magnitude. Again, these are dependent on the person, sort of how good your hearing is, but for a typical person, these are your thresholds of hearing and pain. Those become important when we're talking about sound intensity level. So, if the intensity of sound is 10 times that of another sound, that is, it has 10 times the intensity, then a person really only perceives it to be about twice as loud. So if you increase the power by a factor of 10 and produce a sound that's 10 times the intensity, a person really only would say, well, gosh, that sound is about twice as loud as the previous sound. And because of this, we use a logarithmic scale. To measure loudness, and this is called the sound intensity level. We're going to use L, actually. Sometimes you'll see a beta for sound intensity level, but we're going to use L, which is like level, just to try to keep it straight. So our sound intensity level is equal to 10 times the log of I over I naught. I naught here is our threshold of hearing. Are there two H's? No. Threshold of hearing. So that's that 10 to the minus 12. And then I is the intensity for which you want to know what is the intensity level. Let's just sort of review logarithms, a basic review. So, because we're going to be dealing with logarithms a little bit in this section, and you might not have seen logarithms in a long time. Though if you're a biologist, you'll certainly want to know how to do logarithms because they come up a lot because a lot of natural things are logarithmic. So if we have n and it's equal to a to the x, then we can say then that, so for example, 100 is equal to 10 squared, right? 10 times 10 is 100. So n is 100, a is 10, x is 2. Likewise, 1,000 would be 10 to the third. So I can also say that the log base a of n is equal to x. So if I would write this as the log base 10, and you can do logarithms in any base, but we'll just do base 10 logarithms, which are more common. Or if you know if you're using the Euler's number, which is like 2 point whatever, then that's a natural log. So it's a logarithm, but just to a different base. So here, log base 10 of 100 is equal to 2, right? So here, I'm dealing with the same numbers here. The log of 100 is 2 because 10 to the second power is equal to 100. Similarly, if I'm doing log base 10 of 1,000, what's that equal to? 3, right. Log base 10 of 10,000 is 4. Log base 10 of 100,000 is 5, and on and on. All right? We will not write this. I'll just leave this off. So that's generally implied when you're writing a logarithm. If it's base 10, you don't write anything there. Now, these intensity levels are measured in decibels. And we usually abbreviate this as a D capital B. You might be wondering, actually, gosh, you said this is logarithmic. Then you're probably, in your notes right now, you've probably drawn a circle around the 10, and you've probably drawn like 4 question marks. It's like, why is that 10 there? If this is truly a logarithmic scale, that 10 should not be there. Is that what you have in your notes right now? because it's really puzzling you. The reason is that sound intensity level is not measured in decibels, but it's measured in bells, not decibels. So this deci is not a metric prefix that we use very often, but it is a metric prefix. It's equal to 10 to the minus 1. And because we actually use decibels as our measurement for sound intensity level, that's where that little 10 comes from that you have all the question marks. It's to account for decibels instead of us using bells. Not like bells like the governor, but bells in like a measurement of sound intensity level. Is that his middle name or what? Or is that part of his last name? John Bell Edwards. What is it? Bells. Is it his first name? Is it John Bell? Anyway, a bell is really our unit of sound intensity level, but we use decibels, and that's where that 10 comes from. Okay. Logarithms often confuse students, and yeah, it confuses me too. I hadn't used logarithms in a while to go back and sort of brush up. So make sure that you can solve simple logarithmic problems, and there are some in the homework, and we'll do some in class here as well. So we're working with this equation, right? We have the L equals 10 log I over I naught. As I mentioned, our I naught, that's our threshold for hearing, and we can compare intensities of two sounds. Imagine I want to know what is this equal to. Well, I would say L over 10 equals log of I over I naught. In order to get rid of that logarithm, I would raise both sides to the 10. So I'd have like 10 to the L over 10 is 10 to the log of I over I naught. And then this would effectively cancel out. And so that's where I get this expression. You need to know how to work with these and doing stuff like that. So say, for example, if I give you this and I ask you for I, make sure that you know how to solve for I. Now, like I said, there's some homework problems, and we will do some clicker questions next time on this as well. Just be able to do these logarithms and work with them. It's a useful skill for you in other classes when you see logarithms. Y'all okay with logarithms? You use them in other classes? They're pretty important, actually. So spend some time just sort of learning them. I want you to be able to, do that. Now notice here that if I have a change in 10 decibels, that's this. If delta L changes by 10, say it goes from 10 to 20, then that means that my intensity is a factor of 10 larger. Okay, so that means if I increase L, if I add 10 to L, then I multiply my intensity by 10. So a change in L of 10 decibels results in a sound that's 10 times as intense. So say, for example, I go from 20 decibels to 30 decibels. I go from 20 dB up to 30 dB. That means that my intensity now will be 10 times the original intensity. I increase it by a factor of 10. I don't add 10 to it, I multiply it times 10. Likewise, if delta L is 20, like it is in this example, I go from 30 decibels to 50 decibels, that's going to make an intensity that's 100 times as intense. So if I go from 30 up to 50 decibels, I add 20 to it, then that means I'm going to have a sound that's 100 times as intense. What if I go from, 50 decibels to 30 decibels, or not 30, I'm sorry, to 80 decibels? My intensity in this case will be how much bigger? 1,000. All right, so you're catching on now. So this is 1,000 times as intense. Because my delta L is changed by 30, 30 over 10 is 3, 10 to the third is 1,000. Okay? Be able to manipulate that equation and be able to solve for any one of those variables. So here, if I have two sound levels that are in the ratio of 2 to 1, what is their difference in decibel levels? Well, you can't, that's not a simple thing where it's, if it was 10 to 1, then I could say their difference in decibel levels is 10. Or if it was 100 to 1, I could say that it was 20. Or if it was 1,000 to 1, it would be 30, right? So, but here I have a ratio of 2 to 1. So I start with this expression, I1 over I2 equals 10 to the delta L over 10. And by the way, I don't have your equation sheet yet, but probably all that you're going to have on that equation sheet is this equation right here. That is what you'll have, not this one, which is really just, derived from that one. Okay, so their difference in decibel levels, I have a 2-to-1 ratio, so I have 2 over 1 equals to 10 delta L over 10. Right, I get this because I say this is 2I, this is 1I. 1 is twice that of the other, so I just cancel those i's. And now I want to solve for delta L. So 2 is 10 delta L over 10. I do the logarithm of both sides. I do the log of this side, that cancels that out. And the log of 2 times 10 is equal to delta L. And you do that in your calculator, you get delta L here is equal to 3. All right, so for example, if I have two sounds, one is twice as intense, that means that their difference in intensity levels is 3. So for example, one might be 3 decibels, and then the second would be 6 decibels. Okay? Yeah. Equals right here.
Right there. That's scratched out.
Oh, that was log of 10 to the delta L over 10. Let me write it out. That is fairly important. Because when I have log of 10 of delta L over 10, these will cancel out and just leave this term. Taylor, do you have a question as well? That was it. Okay, great. You'll have a couple questions about this. Make sure that you can do them. They're in the homework. And as I've told you before, really focus on that homework and focus on those questions that I'm going to mail out to you. I'll be pulling test questions. They won't be identical, but they'll be similar. Very, very similar, okay? All right, let's look at the Doppler effect. Probably seen the Doppler effect before, but when the source of a sound, or you've experienced the Doppler effect, I don't know if you've ever studied it, but you certainly experienced it. When the source of a sound is moving, the observer perceives a frequency that is different from the actual frequency. Right, so you have a cop car, or whatever, police car, excuse me. You have a police car. They have their siren on, and they're putting out a sound of a certain frequency. We'll call this frequency 1. It's the actual frequency of the sound, where if the car was actually standing still, then it would have that frequency. But it's traveling towards you at a certain velocity, and so you're standing over here because they're coming to get you. And well, no, you're a little bit afraid. Because you're a criminal. They're going to come get you. Okay? You hear a frequency that's higher or lower than the actual frequency. The frequency that you hear, we'll call it frequency 2. Is it bigger or smaller than frequency 1? Is it higher pitched or lower pitched than the actual sound? It's a higher pitch, right? When something moves towards you, you see this with trains. When trains move towards you, they have a higher pitch. So F2 here is bigger than F1 when it's moving towards you. If it's moving away from you, then it's going to be a lower frequency. Look, I got a little video, or it's not my video, but somebody it's on the internet. So we know that with the Doppler effect, and you've probably experienced that, whether it's been like at the train yard or when the police are chasing you or whatever. Okay, that those frequency observed are different from the actual frequencies. We have a couple of different equations that describe this. I'll provide both of these to you. The observed frequency, when the source is moving, either away or towards you, the observed frequency is equal to the frequency of the source times the velocity of the wave divided by the velocity of the wave plus or minus the velocity of the source. If it's moving towards you, you need to figure out, do I use the plus or the minus? I never remember this. I always have to think through it. If it's moving towards me, then I know that F obs must be bigger than F source. And so which would I use in order to make that happen? If I'm moving towards, or if the source is moving towards me, will I do a positive or a negative here, such that it would make this value bigger than this value? What do I do here? Plus or minus? It's going to be a minus, because I want the denominator to be smaller than the numerator. That means this number bigger than 1, which makes this value bigger than this value. So if I'm moving towards, then I will say VW minus VS. And if I'm moving away, that means that F obs is less than FS. Then I'm going to say VW plus VS. You can memorize that if you want, but I think it's easier just to think about it. What must I use here in order to make the observed frequency either bigger or smaller? If I make this a positive, this value is less than 1. If I make it a negative, this value is bigger than 1. And if it's not moving at all, this value is equal to 1, and the two frequencies are the same. If the observer is moving, it's a little bit different. If the observer is moving, my source frequency times the velocity of the wave plus or minus the velocity of the source divided by the velocity of the wave. Let me actually write that. It wasn't very clear. So VW here is the wave speed, the speed of sound, which will be given, and then VS is the speed of the source. All right? Similarly here, towards or away, think about what you do. If it's towards, I'll let you be thinking about that. What do you want to do? If it's towards, my F obs is bigger than my source. So think about, do you add or subtract? And if it's away, my F obs is less than the frequency of the source. So do I add or subtract? Think about that for just a second. So let's see, if I want to make this number, the observed frequency, bigger than the source frequency, what do I do here? Add or subtract? I want this number to be, add, right. You're right. So if I would do that, I do VW plus VS. And if I want it to go away from me, that's VW minus VS. Okay? You have a homework problem. We're not going to have any clicker problems, but you do have a couple of homework problems for Doppler shift, just calculating the observed frequency. Make sure that you can do those. We're not going to do them here in class. Let's look at a sonic boom. This is the last thing, then we'll wrap up. A sonic boom occurs when the speed of the source exceeds the speed of the wave. It exceeds the sound speed. Actually, it's not actually exceeding. It's more like it approaches the speed of the wave. So you can get this in boats. If you imagine a boat traveling through the water, lakes have a particular wave speed depending upon their depth of the water, the temperature of the water, the density of the water. Waves travel at a particular speed, and those waves will travel out behind the boat, in the wake of the boat. But if the boat is going really fast, that exceeds the speed of the waves in the lake, then it will produce waves at a faster rate than they can get away from the boat. So it produces waves that all bunch up next to one another. They constructively interfere, just like the orcas, right, on the Frozen thing. They constructively interfere and create bigger waves. The same is true for a sonic boom, where you get a jet that's flying through the air, and it just produces these waves that all bunch up next to one another, and it makes that loud boom. You ever heard a sonic boom before? seen the Blue Angels or the Air Force guys or a fighter jet flying, if they approach the speed of sound, they'll make this loud boom sound. I have a little video. It's just oh no, we'll just skip it. It's just jets doing sonic boom. Okay. Y'all have a great day. I will send that document to you.